So we're going to talk for a few minutes about Kepler's third law. His first law was planets orbit in ellipses with the sun at one focus. So we kind of did that just in our last few videos. His second law is planets sweep out equal areas in equal times. We showed that earlier on. That basically said the rate at which the area is swept out is proportional to the angular momentum. And we'll come back to that in a second. And the third law says the square of the period is proportional to the cube of the semi-major axis of the ellipse. Kepler did a lot of work to get this, really to get all of them. And so we're going to show this one using the information we got in the second law, and a little bit more about the ellipse. I've just got to make another definition or two. And so let me remind you that so we're going to take the special case. We want to find out what B is. B is the semi-minor axis of the ellipse, right? It goes from the center up to the high point, and I want to write that in terms of A and the eccentricity. A is the semi-major axis, and if you remember, the semi-major axis is this length, right? And the definition of the ellipse is the locus of points, the sum of whose distance from two fixed points, these points, F and F prime, is constant. And it turns out that constant value is 2 times the semi-major axis. And the way we see that is imagine we have a string looped around here, right? And so I'm going to have it go to this point, except that marker is dead somewhere. So if I loop it around here and go all the way to here, I did this in a previous video, right? Then one length of this is always tied up between the two foci. If I have thumbtacks here, and so the remaining string, if you want to call it, is this length plus that length. It's this length plus that length. And this length plus that length, I can just take this length and put it over here, gives me the full length of the ellipse, the long axis of the ellipse. And that means the slack that I have, r prime plus r anywhere, adds up to 2a. You can just work that geometry out yourself if you want. So in this particular point right here, r prime, it's symmetric, and so they each get an a. So r is equal to a and r prime is equal to a. And that allows me to take one of these triangles, which is a right triangle, and say, look, b squared is equal to, b squared plus epsilon a squared is equal to a squared. Right? This squared plus that squared is equal to that squared, or you can do on the other side, it's the same thing. Right? And so that means that b squared is equal to a squared minus epsilon squared a squared, or b squared is equal to a squared times 1 minus epsilon squared, or b is equal to a times the square root of 1 minus epsilon squared. And so that's what the semi-minor axis of an ellipse is. By the way, if you remember, this distance here was called the latus rectum, and it was equal to 1 minus epsilon squared times a. And so these two differ by a factor of the square root of 1 minus epsilon squared. All right, so we're going to use this little piece of information about b as part of our proof that the square of the period is proportional to the cube of the semi-major axis. So we're still talking about Kepler's third law, and I'm going to start with the second law, which said that the rate at which the area is swept out is equal to the angular momentum divided by the mass, or A dot is equal to angular momentum per mass divided by 2. That's what we got when we solved the second law. And so I'm going to integrate A dot over one full loop. So tau is the period, and that means that that this says the integral of the rate of change of the area over one cycle is just the area, right? That's sort of an obvious statement, and that's the same thing as integrating this quantity over the period. But this quantity is a constant, so when I integrate this quantity over the period, I just get the quantity times the period, and so the area is equal to L over 2 times the period. And now you can say, well, the area of an ellipse is pi AB. Right? That's what the area of an ellipse is, where that's the semi-major axis and that's the semi-minor axis. And so it's if it's a circle, it's pi r squared, but if it's an ellipse, it's pi AB. And so what we get is pi AB is equal to L over 2 times tau, or the period is equal to 2 pi AB over L, right? But we already know that B is the square root of 1 minus epsilon squared times A, and so that's 2 pi A squared times the square root of 1 minus epsilon squared over L. So I've rewritten the period up here. We're just going to have to do a little math on this, right? And so I'm going to square both sides, and I get the period squared is equal to 4 pi squared a to the 4th 1 minus epsilon squared. That's why we squared it, to get this guy out of a square root, over L squared. And then we're going to remember that the lattice rectum alpha is equal to A times the square root, not the square root, A times 1 minus epsilon squared. And so 1 minus epsilon squared is equal to alpha over A. And so I'm going to replace that here, and I'm going to get the period squared is equal to 4 pi squared times a to the 4th over L squared times alpha over A. That cancels that, and that gives me a third there. And then I'm going to use the fact that alpha is equal to mL squared over K, which is equal to, for gravity, that's equal to mL squared over G m, right? Because that's what the K was. The K was, you know, the K came from the f of r is equal to K over r squared. And so the K is just whatever's in the numerator. It's KQQ for electrical forces, but it's GMM for gravitational forces. The m's cancel. And so this gives me the period squared is equal to 4 pi squared a cubed. I'm going to replace alpha with this thing, so it's L squared over G times m, where this would be the mass of the sun, and I have an L squared there. And so those guys cancel, and I get that's 4 pi squared over G times the mass of the sun, a cubed. And so this is Kepler's third law. The period squared is proportional to the cube of the semi-major axis. None of these terms depends on anything except the mass of the object that's being orbited. And so if you write this, if you say the period squared over the area cubed, over the semi-major axis cubed, is equal to 4 pi squared over G times the mass of the object that's being orbited. So if you take the period squared over the semi-major axis cubed for the Earth, or the period squared divided by the semi-major axis for Uranus, or the period squared divided by the semi-major axis cubed for Halley's Comet, you get the same number for all of these things. And so if you know the period of the Earth and the semi-major axis of the Earth, or you know the period of anything, you can calculate the semi-major axis of that thing based on knowing this. Of course, when Kepler figured this out, they didn't know the mass of the sun, so all they knew was the total value of this thing, and so they didn't know what was G, what was the mass of the sun. They didn't have the 4 pi squared. I don't think he did these calculations. It was Newton's. These are all Newton's calculations, of course. All he knew is that this ratio was a constant because of the proportionality. It was Newton who sort of showed all this why Kepler's law works. So as an example, we can say, what's the period of a comet with an with a semi-major axis of 4 astronomical units? An astronomical unit is the average distance from the Earth to the Sun, right? And so we can say, look, Kepler's third law says the period of the comet squared. All right, let me try that again. The period of the comet squared divided by the semi-major axis of the comet cubed is equal to the same thing for the Earth. The period of the Earth squared divided by the semi-major axis of the Earth cubed. And so that's and so if we're looking for the period of the comet squared is equal to the period of the Earth squared over the semi-major axis of the Earth cubed times the semi-major axis of the comet cubed. But that's just 1 year squared over 1 astronomical unit cubed times 4 astronomical units cubed So I know that these ratios are equal for everybody who's orbiting the Sun, and so I can just equate the two, and then I just put everything I know on the right-hand side and solve for the period of the comet, right? And I don't even have to do anything with units. These units are fine. The period of the Earth is a year. The Earth's distance from the Sun, the semi-major axis, is 1 astronomical unit. This is 4 astronomical units. All the units cancel. I'm left in years. 4 cubed is 16 times 4 is 64. That's 64 years squared. Take the square root of that. I get the period of the comet is 8 years. So here's another question. What's the period of a satellite in a circular orbit 200 miles up? 200 miles times 1609 meters per mile is like 3.2 times 10 to the 5th meters. But that's how high it is above the surface. This r is its semi-major axis, and so that's relative to the center of the Earth. And so r is equal to 6.37 times 10 to the 6th meters plus 3.2 times 10 to the 5th meters, which is 6.69 times 10 to the 6th meters. And so now I can just say, look, the period is equal to the square root of this mess, 4 pi squared times 6.69 times 10 to the 6th meters cubed over 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared times 5.98 times 10 to the 24th kilograms. What I get for that is about 5.443 seconds, and if I multiply that by 1 hour over 3,600 seconds, I get about 1.51 hours. So about an hour and a half. There are other ways to do this problem. You could compare. You could say the period squared over the semi-major axis cubed for the satellite is equal to the period squared over the semi-major axis cubed of the moon, right? Because these are two things that are orbiting the Earth. And so if you knew the semi-major axis, you could look these two up, and you could do this calculation and solve for the period of the satellite, and you would get the same number as this. So there are other ways to solve that problem.